In this video, we will go through the simple method of assigning electronic configurations to atoms and monatomic ions. The electron configuration of an atom or monatomic ion describes the number of electrons at each energy level. Each allowed energy level for an electron is represented by a main shell number, also known as the principal quantum number, and a subshell. The main shell number is written as numbers, so the first main shell, the second main shell, the third main shell, and so on. Their subshell is written as lowercase letters, the S, P, D, or F subshell. The S subshell has one orbital that can hold in total 2 electrons. The P subshell has 3 orbitals that can hold in total up to 6 electrons. The D subshell has 5 orbitals that can hold up to 10 electrons, and the F subshell has 7 orbitals that can hold up to 14 electrons. In the most stable state, that is the ground state of an atom or ion, the electrons occupy subshells with the lowest available energy levels, and this diagram shows the energy levels in their increasing order. This is the order in which we fill up the subshells. So 1s is the lowest energy level that is shown here. It increases to 2s, then 2p, 3s, 3p, 4s, going on in this diagonal order. For the first main shell, there is only one subshell, 1s. For the second main shell, there are 2 subshells, 2s and 2p. So the second main shell can hold up to 8 electrons. The s subshell holds 2 and the p subshell holds 6. 2 plus 6 is 8. The third main shell has 3 subshells, s, p, and d. And the fourth main shell also has 3 subshells, s, p, and d. So now we will go through an example. Let's start with the sodium atom. From the periodic table, we see that the atomic number of the sodium atom is 11. This is equal to the number of electrons of the sodium atom. And now we will write down its electronic configuration. So we will start at the lowest energy level, which is 1s. And as we already know that the s subshell can hold up to 2 electrons. So 2, we need to fill up the subshell so that in total we have 11 electrons. And when we have filled the subshells to have 11 electrons, that electronic configuration will represent the sodium atom. And the next one in increasing order of energy is 2s. And the s subshell holds 2 electrons in total. After that, we have 2p. The p subshell holds 6 electrons. So how many electrons do we have? 2, 4, 10. But we need 11. The next one in increasing order is 3s. And we only need to add 1 electron to this s subshell of the third main shell to achieve the electronic configuration of sodium, which only has 11 electrons. To help you with these problems, I would also like to let you know that the periodic table can be divided into different blocks. So this is the first 2 columns of the periodic table represent the S block. The middle chunk of the periodic table, the transition metals, they represent the D block. This block is the P block, and this block at the bottom, this whole part, these 2 rows are the F block. So the sodium atom is here. This is another way to work it out. So this is the first main shell, this is the second main shell, this is the first main shell. So 1, and this is the S block. So for the first one, we include the helium in the S block. So we have 1, 2. So 1s, 2. For the second main shell, we go to this second row that represents the second main shell, and we have 2 elements in the S block. So we write 2 and we have 1, 2, 3, 4, 5, 6 elements in the p block, so we write 6. And we have the sodium, only one element in the s block of the third main shell, so we write 1. So this is another way to work this out. So let's go through another example. Let's do the iron atom now. So if we look at the periodic table, the iron element is over here, and its atomic number is 26. So the total number of electrons in iron is 26, the same as its atomic number. Now we will start to fill the shells in increasing order of energy. So the lowest energy level is 1s2, then we have 2s2, then we have 2p6, then we have 3s2, then we have, in increasing order, we have 3p, and the maximum number of electrons that the p subshell can hold are 6, so 3p6. After 3p6, we have the fourth main shell, so the s subshell can hold 2 electrons. Let's see how many we have done. 2, 4, 10, 12, 18, 20. We still need 6 more to achieve the electronic configuration of iron. So after 4s, we have 3d. So the d subshell can hold in total 10 electrons, but we only need 6 for iron. So we will do 6. So you could have also done it through this method. So 1, 2, 3, 4, 5, 6. So this is the electronic configuration of iron. Now we will do an example to determine the electronic configuration of a monatomic ion. So let's find the electronic configuration of calcium ion, which has a 2 plus charge. So first of all, we will find the electronic configuration of the calcium atom. So the calcium atom is over here and it has 20 electrons. So calcium has 20 electrons. So we need to fill the subshells to have 20 electrons. So let's start from the lowest energy, 1s2, 2s2, 2p6, we have 10, and then we have 3s2, 3p6, we have 18, and then we have 4s2. So 2, 4, 10, 12, 18, 20. We have 20 electrons for calcium, but note, this is the calcium ion, it's not the calcium atom. And this has a +2 charge, which means 2 electrons have been taken away from the calcium atom, leaving it with a +2 positive charge. So we have to take away 2 electrons. So this would be the electronic configuration for calcium, but for the calcium ion with a 2 plus charge, we have to take away these 2 electrons. So this is the electronic configuration for the calcium ion. Now let's do an example with a negative ion. So let's use bromine, the bromide ion, as an example. So from this periodic table, we can see that bromine is over here and it has 35 electrons. So bromine has 35 electrons. So we will start writing the electronic configuration of bromine starting from the lowest energy level. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, So if we go on back to our diagram, after 4s2, we have 3d, 4p, 4s. So 3d, 10. So up till now we have 2, 4, 10, 12, 18, 20, 30 electrons filled up in the shells. The next energy level from the diagram is 4p, and we only need 5 more electrons. We have 30, so we add 5 to this last subshell with the highest energy for this example. But note that this is not bromine. This is the electronic configuration of bromine, but we have the bromide ion, which has a negative charge. It means that this ion has taken an electron from another atom. It has one extra electron, and so we also need to add this extra electron to the electronic configuration of bromine. So we don't have 4p5, we will have 4p6. And this is how you write electronic configurations for ions. Whenever you have a positive ion, you take away the number of electrons equivalent to the positive charge on that ion, and when you have a negative ion, you add the number of electrons equivalent to the negative charge on that ion. Now this is how we calculate electronic configurations. However, just before we end this video, I would like to tell you that there are 2 exceptions to this method of writing down electronic configurations, and these include chromium and copper. Chromium has 24 electrons and copper has 29 electrons. The only exception for these 2 elements is that in the S subshell of the 4th mean shell, instead of having 2 electrons in this S subshell, they both have only 1 electrons. So chromium and copper only have 1 electron in the S subshell, and they go on to have chromium goes on to have 5 electrons in the D subshell and of the 3rd mean shell, and the copper goes on to have 10 electrons in the D subshell of the 3rd mean shell. This is only so that these atoms can obtain a more energetically favorable state. So we have 5 orbitals in D. If each of the orbitals are occupied by a single electron, then it's more energetically favorable than the S subshell of the 4 main shell having 2 electrons. But these are the only 2 exceptions, and this is how we calculate electronic configurations of atoms and monatomic ions. I hope this helped you. Thank you.